Welcome to this session on IoT in the cloud, building and unleashing the value in your renewable energy system. As mentioned, my name is Mark Heckler. I'm a principal technologist and developer advocate with Pivotal Software, Inc. Pivotal is the maker of Spring Boot, the Spring Framework, Redis, Rabbit, Greenplum, huge contributor to Cloud Foundry and the Cloud Foundry Foundation, a huge contributor to Apache Tomcat and a handful of other things. We like to refer to ourselves as a tiny little startup in Silicon Valley. Pivotal recognizes the opportunity and challenge of incorporating millions, literally millions of new devices, producing data and interactions into the existing and new business models. This session is just one peek at one facet of that. They took it down, but I blog somewhat frequently, less frequently than I would like, at my personal domain, thehecklers.org. I tweet very regularly at mkheck on Twitter. I live on Twitter. So if we only have a very brief time here, typically the best discussions happen afterward because we have unlimited time after that. So if you have any questions, if I hit something kind of quickly, if I glossed over something, entirely possible in 25 minutes, please do reach out to me via Twitter. Or if you're not on Twitter, I'm also a member of the slightly older and more established social network called email. Please do reach out to me on email. That's an option as well. So a little bit about me. I am a longtime developer, Java champion, so recognized by my peers for contributions to the Java community. Appreciate that. And I've been kind of around the world speaking. I really appreciate the opportunity to speak here. So the things that I'd like to discuss today, in no specific order, we'll iterate at speed in a very tight loop. Kind of what's involved in an IoT project. And this is from a developer perspective, an architecture and development perspective. So this is more in the terms of a prototype or a minimum viable product, if you will. How would you approach one? And then I kind of break it down on what all of the components that would be involved. And then I throw in a short demo, hopefully at the end, so we can get to that. And then answer any questions that we may have. Again, if we run out of time or if we just run out of time for additional questions, please do reach out to me. Happy to answer them and talk at length on any of this. So an example IoT architecture that I kind of followed with all of this, and I think it's a good reference point. Everyone always talks about the Internet of Things, and they focus first on the T, the things. So let's start there. Typically, you have some variety of sensors and devices and actuators, things that interact with the physical world. And controlling those or feeding into those and communicating with those is some kind of a microcontroller typically, or a microcontroller-based device. I refer to those as hardware loops because they're very good at a specific set of tasks, typically looping through and communicating within devices. Then you typically have something along the lines of an IoT gateway. The gateway provides kind of an aggregating function for the various different devices and end devices, endpoints. And it also provides the connectivity upstream. So typically, the gateway serves a few specific functions like security and access control, communication, transformation, because you may gather data from all of these various different nodes and somehow manipulate that data and package it for an upstream push, or vice versa. And then, of course, you should be able to deploy updates to that IoT gateway, and hopefully, if you have a capable gateway, it should be able to push up updates downstream as well. Tying everything all together typically is some kind of a cloud platform. I usually again, people always fixate on the T, the things, but without the I, and there's a reason the I comes first, Internet of Things. Without the I, typically we have what I like to call the islands of misfit toys. They're useful, the devices serve some purpose, but without the cloud platform to tie it together, the value is extremely limited. So on top, we have a cloud platform that handles things like providing services. I discuss a microservices-based backend as we go. Provides data stores and message queues or brokers and certain interfaces that are needed to interface both with your gateways as well as the outside world, your user interfaces. And typically that communicates with the IoT gateway and vice versa via standards-based communication. So REST over HTTP or WebSocket and things of that nature. So is anyone here familiar with the concept of domain-driven design by Dr. Eric Evans? In the development community, this is a huge deal. If you've heard the term microservices, this is something that's discussed kind of in the same breath. Eric Evans produced the seminal work on this. There's a concept called bounded contexts. And as it says at the bottom, as Martin Fowler mentions, domain-driven design deals with large models by dividing them into different bounded contexts and being explicit about their interrelationships. This helps us define more precisely what we're talking about within a certain domain. And typically this is used to discuss large enterprise systems, but it works really well as well when you're talking about an IoT system with something like that. Oops. Tricky. Because when you break these out into different boundaries, you start being able to iterate much more quickly on the development path within each level. So, breaking it down to a real-world context, the United States is an example, a real-world example of bounded context, because each member state has its own context, things that apply to it, things that apply to the citizenry within a particular state, but then you also have a certain set of shared responsibilities and shared concerns that are handled at a federal level. And the same thing goes with bounded contexts as well. So again, approaching an IoT system in this way improves the fidelity of each context model and capabilities and increases quality while enabling you to increase development speed. Now, the system that I am going to show you and demonstrate and talk through today, I kind of treat it as a prototypical system. I created a renewable energy system at my house and put it in a power production building. I call it my powerhouse. It's a small utility shed where I have everything kind of funneling in and then feeding the rest of the systems. But I wanted this to mirror a full-scale system, an industrial system, even though it's a much smaller scale. I wanted the same lessons and the same steps to go through so that you can learn from each step, each component, if you will, as it comes together. So to me, the keys to a valid proof of concept is that it mirrors a full-scale system, a large industrial system. Even if you make different design decisions, you should be aware, you should be aware of what the trade-offs are that are involved, the pros and cons. It should be scalable by default, so that as you go, you can apply the lessons. You can even sometimes apply the technologies wholesale, or if not, certainly key components of those as you scale up or scale out. And it should be widely composed of widely available components, because if you're talking about a prototype system, you need something you can get a hold of quickly and move out on quickly. So we start first with the microcontroller level. I show an example of an Arduino, but again, there are many different microcontrollers on the market. Actually, the market's consolidating a little bit now, so that may not be the case here in a year or two. But here are some of the criteria that I used for my prototypical system. These, again, are very important from a development perspective because you can iterate quickly. If something breaks, you can quickly grab another off the shelf, order it in, what have you. You also have the ability to deal with a large support community. So if you have questions, usage questions, or library interaction questions, you can quickly get some feedback from that, and usually a quick fix. Some of the criteria that I had, it should be all open source, hardware and software if possible, but certainly everywhere possible. Add-ons should be plentiful, because the more add-ons you have, the more interactions you can have with different devices in your network. Programming language and environment should be fairly flexible, and certainly fairly understandable and common to your developers, so they can be very quickly productive. Whatever microcontroller platform you standardize upon or use, it should be available in various configurations. One size typically fits none, so you want some options in that regard. Should be durable and reliable. If you place an industrial IoT system into production, typically it's not down on the floor where everyone can get to it. It's up behind a panel on the wall. I sometimes refer to liquid robotics, which is a very remote and distributed IoT type of system in which drones, ocean-going drones, have on board a full complement of technology. It's hard to go kick the box when it's in the middle of the Indian Ocean. So, and of course, low power requirements, because with any system, with any IoT system, typically the goal is not just to have an IoT system, it's to do something with it. A greater purpose. So the more power that you drain off for your IoT system, the less power is available for everything else. Next, we'll take a look at an IoT Gateway. Typically, you have the same requirements for that you would for your microcontroller devices. However, I look at a few things, and from a development perspective, these are extra pluses. These are bonuses to have. The Linux operating system, very nice. Gives you a lot of capabilities, which I kind of go into as we go. But remote access, secure access, things that you kind of get bundled in for free in many ways. It also is something that's very standard, and most of your development team will already be very well acquainted with it. It should support all major programming languages, so you're not tied to a particular language or set of implementation details per se. Communication and protocol options should be varied. The more options you have, again, the more options you can employ for your particular set of circumstances. You want your IoT gateway to be remotely and securely accessible. Again, you don't want to have to go out and visit the various warehouses and climb up on a ladder just to get to them. And inexpensive add-ons are kind of key, because that way, whether it's in production or even just in development, you can quickly get the parts you need without breaking the bank. For a back-end service, and again, this is where it starts to get kind of key, because everything up to this point is very easily swapped out, and it gives you some value, but certainly you need something that gives you maximum value. So the things that I looked at, and again, I work for Pivotal, so this probably won't surprise anyone, the technology stack that I chose. I used Spring Boot to create various microservices and to deploy them on Cloud Foundry. Really, your back end, your cloud system, is primarily used for three things, and everything else kind of fits under those or adds onto those: communication, query, and storage. And once you start with that and establish, again, your minimum viable product, you can build out very easily from there. I wanted an open source development platform, so that way I could see the code, get to the code. I wasn't necessarily tied to a specific vendor's implementation. In addition to being able to see what's going on behind the scenes in case I ran into an issue. I wanted a versatile open source cloud, so I would have some latitude in where I deployed or how I deployed as well. And I wanted something that would enable velocity in development, again, portability and where you deploy it, and certainly simplicity. And Spring Boot and Cloud Foundry provided a lot of that. Spring Boot lets you bundle your application into what's considered an Uber jar or a fat jar, where you bring all of your dependencies with you. It's the ultimate in Java portability. Is anyone here familiar with the concept of 12-factor applications? 12-factor apps helps. It defines 12 factors, obviously. The two that I kind of refer to the most is externalizing your configuration, so that you don't bundle in credentials and backing service directives and things like that. That if you re-platform, if you re-home, that you have to rebuild your software. That's a very time-consuming task and not something you want to do in case of an outage. It also is that another factor is you bring your dependencies with you, which again increases that portability. So whether I'm deploying to one flavor of Cloud Foundry or another, or even a local JVM running on a set of servers, it's all possible to do with no changes in how you're building your application. Certain standards like Spring Data REST, HATE-OAS for hypermedia-driven applications, things like that. You can quickly create REST endpoints, WebSocket support, things of that nature. Allows you to get up to speed and, again, build that minimum viable product very quickly. For a front-end application, I wanted something that would be available anywhere, and this is something that typically applies in full production, full-scale systems, because you don't want someone to have to come into their office, sit down at their desk in order to adjust something or react to something that may have broken. You want this to be available pretty much from anywhere, if at all possible. I wanted to choose something that would run on every client with a lot of library and framework support, and again, run that on that versatile open source cloud. So I chose a combination of HTML5, CSS, and JavaScript running on Cloud Foundry. And then just for fun, and to see how far we could take this exercise, I wanted to build in a wearable application. This is kind of a hint of where I'm going with this as well, because we're kind of just starting to crack the outer edges, aren't we? I mean, we've got some really nice control panels. We have some really nice visibility into our IoT systems. But the control, I mean, again, even when you have to pull it up on a laptop or a tablet, wouldn't it be nice to give the ultimate in control to somebody who's responsible for these things, to allow them to control things from their wrist or by voice? So I wanted something that would give you the ability to monitor and control very simply and subtly an IoT system. And I think this is really where we're headed, isn't it? I wanted also something that would have ease of development and a lot of library and framework support. You have a lot of different options. I chose to do the version 1 on a Pebble watch, which allows me to do everything in JavaScript. So if I need to access REST endpoints, if I need to encode and decode JSON, if I need to use WebSocket, I can do all that from my watch, and you'll see that here shortly. Also, and this is just a sneak peek, in the future I want to have full voice control and command, and we're underway with that now. So maybe next time we can talk about that. So, whoops, here we go. This is a kind of a look at my prototypical system. And I did forget to say, though, that the diagram that I showed you earlier, in which the gateway is broken out from the microcontroller devices, you're seeing some of that collapse in the home market and in some of the industrial markets as well. However, by collapsing those, you're taking on a different set of pros and cons. So as long as you're aware of the things that you gain and the things that you give up by bringing all of those together, that's perfectly fine. I like to keep them separate because I think it does mirror better many industrial configurations, as well as giving you that extra security boundary at the IoT gateway position. So here's a quick look at kind of what I have in terms of a configuration. In my utility shed, my power generation shed, what I have is the IoT Gateway co-located with a node concentrator, a microcontroller device, which is tied to various different endpoints. So I have a full weather station to monitor the ambient circumstances around rainfall, wind direction, wind speed, temperature, ambient lighting, atmospheric pressure, and things of that nature. I live in St. Louis, by the way. I'm not that far from here, but it gets really warm and sticky and nasty in the summertime at times, and kind of rough in the wintertime at times. So I wanted some way to moderate the environment around my devices, because again, you want robust and rugged components, but you also want them to last as long as possible. So when the temperature gets to a certain point, it will kick on a fan and blow some air across the equipment. It also opens windows, because I have actuators connected to relays that will go ahead and open windows so you get some airflow through there. If the temperature drops to a certain point, it will turn on a heater. If it's in between those two ranges, typically it just turns on a status light and life goes on merrily. I do also have an interior light, so that if I need to go out and check it at night, I don't have to grab my torch or my flashlight. I can just turn on the interior light and be lazy and walk out there. So it's very nice in that regard. But certainly for real full-scale production environments, you would have some kind of a control as well for environmental circumstances. And then let's see. Of course, when you generate electricity with renewable energy systems, that electricity has to be consumed at the time of generation, or it has to be stored in some way. Typically what happens is you create a large array of storage devices, which we call batteries in the real world. So you have some kind of a deep cycle array of batteries that the energy is stored in, so when the sun isn't shining, the wind isn't blowing, that you can still power things. I have both. I have a small wind turbine as well as a series of photovoltaic panels that feed into this. And again, the IoT system should draw, in every case it does draw, about 2 amps or under. Because you don't want to siphon off all your power just to power the system that monitors it and manages it and gives you the ability to act on it if you need to. So really quickly before we get too much further, this is kind of a look at the control panel that I've created. This is the HTML5 JavaScript control panel that runs. And as you can see, there are various different readouts, as well as a panel that you can use to interact with the system. I'm going to actually show you that live and working, hopefully, unless something breaks. Demo gods have been appropriately offered. And this is an emulator that I use to show kind of how things look, again, version 1, early prototype stage of the Pebble wearable application, which shows effectively the same set of readings, and then it gives you the ability to control it from directly on the wrist. what I'd like to do is show you how all of this ties together, because this is kind of key. When you have a system, you don't want to necessarily, again, limit your options. So this is a look at the overall panel. Let's see if I can, because I just opened my MacBook and didn't refresh. Let me reload the page. And there we go. That gives you a look at the, at least the nucleus of the equipment that's sitting in my power generation shed. And then of course we graph the data as it's realized. I also have another application that actually just does long-term graphing. But for today, this is where we'll concentrate. And as you can see here, and I will go ahead and do this here, we can take it out of autonomous mode, in which it operates most of the time within a certain set of boundaries and ranges. And then if I want to turn on the power, of course, I can do that. And you see the fan kick on to give it a little bit of airflow to keep things from overheating. I can shut that off. The little green lamp down here is my status lamp. So when nothing else is happening, typically you see that. And we can shut that off as well. Turn it back on, so on and so forth. Now what I'd like to do at this point, and I'll just leave it there, is come around and give you a quick sneak peek at the application. And this is, I think, as we start to see more and more deployments of IoT systems, you're going to see more control in a smaller scale. And again, the voice app is coming on, but this is kind of a neat look at how things work, Dick Tracy style. So as you can see, the first set of panels here, if I take it to the next, let me, well, we'll come back to that, because I wanted to show you kind of how everything lines up. But if you go into the controls, you can see here that we have a control mode, and right now it's showing that it's in manual override. But if I take, I'll start here first turning on the interior light. And as you notice, everything's tied together via WebSockets. It's fully standard based. So there's no worry about a proprietary stack that you have to adhere to. It's all, again, controlled by you, by worldwide consortiums. And again, you can turn that off. Everything updates. The light goes off. We can go up here. We can turn on our power if we want to. And of course, it kicks on. Turn it off. Everything, again, is fully synchronized. So if you update it from one place, you don't have to worry about everything not reflecting the current state of reality as it is. And again, we'll just go ahead and turn this back to autonomous mode. Nope, I just got a notification, so I'll take that off there. Don't want everybody reading my tweets from my watch. So, OK, so that's kind of the quick tour. I do want to go back. Oh, there we go. Actually, let me. I didn't think this through very well. My control hand is my left hand, so let me slide that over and bring this back. And of course, you can see the same set of dials, the same set of readouts that you would get. I break it down with 4 on a screen just to make it a little easier to consume. Again, when you develop for a smaller interface, you have to approach things a little differently than when you have unlimited screen real estate. And of course, the design is fully responsive, so it adjusts as needed to your screen size. Again, these are very much developer-centered links. The bottom one is kind of the most important one probably, because that gets you to the various different code platforms for the different levels. And if you have any questions, please do reach out to me. Twitter is where I live. Email mark@thehecklers.org as well. So thank you for your time, and thanks for coming.